Hi everybody, this video is about solubility, so we're going to use Table G and Table F and make sure that you understand how to do this. So first of all, here's Table G, and I thought I would go through some sample questions since we've already done it in class, but sort of as a little refresher. Here is all of my solutes. My first question is, what is the difference in solid and gas solutes in solubility as you increase the temperature? So I'm going to take something like KNO3. I'm going to try and use this pen. This might not be great, but work along with me here. All right, KNO3. This is a solid solute, and you'll notice that as the temperature goes up, the solubility goes up. And the reason for that is kinetic energy. As the molecules move faster, they're going to collide more, and they're going to be able to dissolve more particles with a higher temperature. Now, if I instead look down here, I'm going to scroll down a little bit. I am going to choose one of these curves that slopes downward. So right here, you see one swooping down, and that is ammonia. And that is a gas. And so as the temperature increases, this gas decreases in solubility. And the reason why is also kinetic energy. As you speed up these particles, gas molecules escape. So they're less likely to stay soluble in the solution. They don't form spheres of hydration. Instead, they evaporate out of the solution. So that is why you see them decreasing in solubility. You can always refer back to the pop example. If you had 2 cans of pop and you open them up, they have the same amount of gas in them at the start. And if right away you measure that amount of dissolved carbon dioxide and you place one in a really cool room like a chiller, a freezer or something, and then you place the other one in a really hot area, the gas will escape out of the one in the hot area and the pop will become flat, whereas the one in the really cold area is going to keep its carbon dioxide and remain carbonated. All right, let's move on to the next question. Is KNO3 or HCl more concentrated at 50 degrees? So this is what I need to do. First of all, I'm going to change my color ink here. I'll go to green, and I need to find KNO3. There's KNO3, the same solute that I was just referring to, and HCl. Here's HCl right here. And what I want to do is go to 50 degrees. So here's 50 degrees right here, and if I follow this line up, here's where KNO3 crosses, and here's where HCl crosses. So KNO3 is definitely more concentrated because it has a larger number of grams per 100 milliliters of water. So you can think of concentrated as like if you're going to drink a cup of Kool-Aid, if there's more sugar in it, then it's more concentrated. If there's less sugar in it, it's less concentrated. All right, number 3. How many grams of NH4Cl must be added to 100 milliliters of water at 40 degrees Celsius to form a saturated solution? So saturated means I want it to be on the line, and NH4Cl, I want to find it over here. So there it is, NH4Cl. Here, I'll switch to a new color. All right, so I've got NH4Cl here, and I want to go to 50 degrees. Oh, no, I'm sorry, 40 degrees. So I go here to 40, and I go up, and this is where it crosses. So I go across. That looks like it's about 47 grams. Now remember, you're given a leeway of about plus or minus 2, so it's okay if you said you think it's more like 48. And I also just want to point out that there's 100 grams of water in this solubility chart, and it asked me per 100 milliliters of water. All right, the next question. A solution contains 10 grams of SO2. So just to make things a little easier right now, I'm just going to take my eraser for a minute because I'm making a mess out of the screen. So let me just try and get rid of this. Okay, go back to a pen here. Sorry, first time using this with the pen. All right, so I want SO2 at 10 degrees Celsius. So I go down here to 10 degrees and I go up to SO2. There it is. I would say it's around 15. And a solution already contains 10 grams of it, so how much more has to be added? I would go, it can hold 15, I already have 10, so I could add 5 grams more. That would be the answer to my question. All right, I have a couple more of these problems just so you get used to any that might come up. This one says, how many grams will settle out? If it's settling out, I've gone over the saturation line. And it has 120 grams of NaNO3 in 100 milliliters of water, so I'm keeping the water the same, at 30 degrees. So here's my NaNO3, and I just need to scroll down here a little bit to see where my 30 degrees is. Okay, so 30 degrees, and I'm right there. So I would say that's about 95, and it says that I have 120. So 120 minus the 95 that it can actually hold, how many are going to be sitting out at the bottom? That would be 25 grams would be settled down to the bottom of the container. All right, how many additional grams of KCl, so let me change color here again. This time I'm working with potassium chloride. How many can be added to a saturated solution at 10 degrees in 100 grams of water if you heat it up to 70? All right, so here's my KCl, and here's where it is at 10 degrees. So it's starting out able to hold 30 grams. And at 70 is what the question's asking me. At 70, it can hold about 48. So 48 minus 30, I can add 18 grams more of potassium chloride as I change the temperature from 10 degrees to 70 degrees. All right, last one. Change it over to a new color. All right, a solution of 100 grams of, so I'm starting off with this many grams, and it's KClO3, and it's in 300 milliliters. Okay, as soon as I'm reading this, I'm going to circle it. 300 milliliters of water is not normal. It's normal to have 100 grams of water, so I've got 3 times the volume of water going on in my beaker, and it's at 40 degrees. How many grams are needed to make the solution saturated? So I want to find KClO3. There it is, and I'm at 40 degrees, so at 40 degrees, it can hold, let's say, 15. Sorry, this keeps coming up on my screen. All right, so it can hold 15 in 1. So first thing I want to do is multiply that by 3. So that's telling me that if I have 300 milliliters of water, I can hold 45 grams. It tells me that the solution has 100 in it. So how much is needed to make the solution saturated? The solution is already saturated. The question is not a good one. It should actually be how much is going to settle out, because I have more than I need. So I would take the 100 grams that I already have. It can hold 45. So that means 55 grams are going to settle out to the bottom. So I already have a saturated solution if I have 100 grams in there. All right, now let's move on to something else. Not everything is soluble, so I want you to remember that like dissolves like rule. If things are going to be soluble, solutes and solvents have to have the same type of polarity. So if something has charges, it's polar or ionic. So things that have charges will be attracted to other things with charges. So if you have a polar solute and a polar solvent, perfect. They are miscible, which means they will be able to dissolve. If you have something that is ionic in a polar solvent, it also has charges, so it will be able to dissolve. But if you take something that's nonpolar, it is not going to be very soluble in a polar solvent. So you can only mix nonpolar with nonpolar to have it dissolves. That's the like dissolves like rule. All right, now something new. There are some compounds that are simply insoluble. They do not dissolve in water, either due to their polarity or just due to their chemical nature. So in order to figure this out, we use a new table, and it's table F. And I wanted to show you just a picture. This is what it's called. We mixed 2 liquids here, but the white that formed is one of the products. So it was either a single replacement or a double replacement reaction, and the substance formed is called a precipitate. A precipitate is a solid generally, and it does not dissolve. So those are our precipitates, and we're going to do a lab on that tomorrow. All right, next page. So, how do you determine if the products of a reaction are soluble or if they're insoluble and they're going to form a precipitate? So, first thing you have to do is write out your reaction and determine the products. This is going to be a nice review because you'll have to crisscross and you don't really have to balance, but you could always practice balancing if that was a struggle for you. The second thing you do is you want to look up the products on table F and you want to see if they're soluble. If they're insoluble, then they're going to be a precipitate. So I thought we would do a couple together. Here's what the table looks like. So on this side, you'll notice it says ions that form soluble compounds. So these ones will all dissolve. Anytime you have a group 1 ion, it will dissolve in a solution. Same with ammonium or nitrate or acetate or hydrogen carbonate. No matter who it's with, it is going to be soluble. Down here, halides are usually soluble, but you notice that they have some exceptions. If you put silver, lead, or mercury with a halide, it does not dissolve. It will form a precipitate. So an example, I could write one over here. If I have AgCl, silver chloride, it actually is a precipitate. It doesn't dissolve. It would be followed with a little parentheses with an S for solid. Instead, things that dissolve have that AQ after it, meaning it dissolves in the water. All right, and then here we have sulfates, and when they're combined with silver, calcium, strontium, barium, or lead, they also do not dissolve. With everybody else, they are soluble. These are our insoluble precipitates that could form. On this side, you'll notice that there's new wording. This side it says these are insoluble compounds. So anytime you have carbonate, it does not dissolve. It forms a precipitate, except, so over here in the exceptions column, if you put it with a group 1, so like if you put it with sodium or lithium, it's fine, it will dissolve. But if it's not, then it will be an insoluble precipitate. So that's the way that table F works. Let's do a couple examples. Here I have sodium sulfide with calcium chloride. And so the first thing I want to do is finish off my reaction. So I'm going to go back to my old habits because habits are a great thing to have us repeat and make sure we do it right. Here's my metal. Here's my metal. Metals always want to come first, and the metals want to go with the nonmetals. So I'm going to have this one react with the Cl. I'm going to have the calcium react with the sulfur. So I am going to put Na here, and I know Na is a +1. And I'm going to put my Cl here, and I know Cl is a -1. I crisscross, and I get sodium chloride. NaCl is one of my products. The other product, again, I put the metal first, and I look up calcium, and it's a +2. And I look up sulfur, and sulfur is a -2. So they're another perfect match. I would get CaS. These are my two products. Now I have to flip back to table F, and I want to look up these two products. Oops, I got to remember what they are first. All right, salt. I know salt is going to be soluble because you've seen salt in water, but here's the proof of it. Na is soluble with no exceptions. So put Na with Cl, and perfect, it dissolves. The next one was Ca with S. So there's no Ca over here. There's no S over here. Go over here. There's an S. So I'm looking for some part of the formula. So S is insoluble unless you put it with a group 1 ion. Calcium is not a group 1 ion. So that means this compound that we formed here, this one right here, this is going to be insoluble, which means this is going to be my precipitate. Right? So if we actually combined this, this was aqueous and this was aqueous, so these would both be solutions in my tube. And when I form this new tube, I am going to have something that settles out. And it is either going to sink to the bottom or float up to the top. That's my precipitate. All right, let's try one more together. Here I have lead nitrate and I have magnesium sulfate. So first thing I want to do is figure out my products. So I underline the metals. I say Pb is going to match up with the SO4, Mg is going to match up with the NO3. So Pb, over here I know it was a +2 because it crisscrossed down to here. And if you look up NO3, NO3 is a -1. So Pb is a +2, and SO4. I go ahead and look on table E, and that's a -2. So PbSO4 will be my one compound. And my other compound, Mg, is a group 2, so I put a +2 charge on it. NO3 is a -1. So this would form Mg parentheses NO3, 2 of them, magnesium nitrate. So now I need to go back to my table and look these up. So here I go. Here's, let's see, Pb with, I just forgot what it was with, SO4. All right. Here's SO4. So SO4 is soluble except, oh, here it is, except when you put it with lead. So here, this one is going to be insoluble, which means this will be my precipitate. All right, now let's check this one, MgNO3 2. NO3 is right here. NO3 is always soluble no matter who you put it with, so that one will dissolve. It will not form a precipitate. So I can go ahead and say this one over here, this one is going to be soluble. All right, I have plenty of practice problems for you to do on the worksheet, and if you have questions, let me know in class tomorrow.